Добрый день. Слышно что-нибудь? Неизвестно.
Так,
Алло. Раз, два, три.
да.
Да, видите ли вы доску?
Я вижу доску.
Да. Значит, там на странице со 2 по 8 остались от предыдущего какие-то ерунда какая-то. Значит, а первая страница свободна и начиная...
Упс.
Нет, вторая, кажется, тоже свободна.
А ссылка-то где на нее?
Сейчас пришлю ссылку. Смотри. А,
Я забыл. There is a song.
линк. Сейчас, прошу прощения. Да?
Okay. There should be
Ничего.
translation. Okay. Use voice. This is fine. This is fine. Okay, yeah, then and the door is not closing perfectly, but no, I just not just we don't want to make it that I have. Okay. I start here.
Я послал в чате, сейчас я пошлю сообщение тоже. В этом самом.
Чат, где он мне откроется? А, вот он. Да, еще успеть перекусить. Так, ну что, пишет? Ну, я не знаю, что-то вроде там, может, получается, чтобы было неравномерное с экспертами, но надо проверять. Я так
Да.
не готов
Но,
сейчас.
но,
Ну,
но как сделать корень, не ясно.
ну, кажется, надо как-то просто, значит, нужно просто на разные веса умножать тех и тех, наверное. И все равно хотеть, чтобы, ну, мы просто хотим, чтобы недовольство уменьшалось наименьшим образом. Увеличивалось как можно меньше. Выбирать из двух вариантов, которые увеличивают. Ну, там надо как-то подобрать параметры, может быть, что-то подберется, а может, нет, надо проверять. Я, конечно, могу сказать, что, ну, это там получается, но я сейчас расскажу только для простоты симметричный случай.
Нет, но это я думаю, что не надо так.
Но
Это
врать
есть
не надо.
в книжке Литлвуда «Математическая смесь». Написано, что он с каким-то то ли своим учеником, то ли еще с кем-то, он обсуждал это самое, его текст этого человека. И
Угу.
этот человек писал, что, предположим, для простоты что? А Литл Вул старался ему объяснить, что если так пишут, то обычно имеется в виду, что автор знает, как рассматривать общий случай, но читателя щадит. А если автор сам не знает, то нельзя писать, что, предположим, для простоты. Но там не написано,
Да.
кто этот самый был человек.
Ну, Littlewood это дело такое.
No, in the same book, which is called Mathematicians Miscellany, there are another stories, and one of them I also remember. Just his remark about some paper or thesis or whoever, and he quoted Joseph Haydn, who said that you never should make fun of some sonata of a Grand Duke because you never know who was its actual author.
Sonata of whom? Grand Duke?
Ну, это самое. Не надо делать недовольные мины при звуках сонаты великого князя. Вы не знаете, кто ее в действительности написал. This was the quote as I remember it. But of course, one should look in the
Да, а это мы все под запись рассказываем, да?
Чего?
Да.
Мы это все под запись обсуждаем.
А дело в том, что это всегда записывается.
Понимаю,
хотите
да.
вы или не хотите, все равно все записывается.
Не, но потом надо освоить базовые
навыки отрезания.
Навыки видеомонтажа,
да.
которые даже можно в YouTube делать.
Ну, в YouTube я не знаю, но это самое действительно в OpenShot можно, но при этом, к сожалению, этот самый файл удлиняется раза в 4, поэтому его потом загружать очень
там
сложно.
в YouTube можно, чего там уж напрягаться. Надо, оно там какое-то время что-то думает, но потом это обрезает. Надо только научиться. Я это делал когда-то.
Да.
Так, а что тут у меня?
So Peter Gach, who came from Moscow, he wrote a paper, a Russian Boston paper, and there are on the first page there is an announcement, что какой-то человек, there is some name, хочет избраться в комитет партии.
Добрый день.
Yeah. And actually, it's about the Republican primaries or whatever in Massachusetts.
Со временем.
Yeah, it's time to start, but since there is no Vereshchagin, we should wait.
What a disappointment.
Чего?
They run out of water.
В кране нет воды? That's bad.
В кране нет воды?
Да. Окей. Let's wait still a few minutes.
Ай-яй-яй-яй-яй.
Вот Леша.
Здравствуйте.
Добрый день. Just as usual, if there is a chance to switch on the camera, it's useful for the speaker because he sees immediately the expression of disgust.
Well, then
on
I
your
have
faces.
to make right now. I don't see anybody when so how to arrange Zoom so that I can see.
Sasha, I don't know about other speakers, but me personally, I cannot see on these small pictures and see nothing, and expressions are unclear.
No,
So
but
your claim is a sort of religious ritual.
But okay, today Sasha is a speaker himself, so we can trust him.
No,
Yes.
No,
it's more
it's not
Sasha
correct.
Palachinsky, but still.
Yeah, but there is a view on my screen, and then I can choose gallery, and then I see 10 people.
How I can choose gallery then?
Yeah.
Yeah,
And usually it picks the one with camera on,
yeah,
and so it can see angry faces.
yeah.
Okay, whatever.
Or happy
Okay.
faces.
Okay, so I can start some before Vereshchagin comes. I can start some general explanation. So I already
No, I wanted to start the general explanation. What's the we discussed this, no?
Okay.
Yeah, so
you want to take
I
the
want
shame yourself. So please,
yes.
it's very easy. Let's
No, because suddenly I have to make a talk, so then let me make the talk. So okay, so we were discussing this inequality of Shen and Ramashchenko, I guess, or whoever. That well, so if you have okay, let me try to state. So so if you fix n and you fix a combinatorial rectangle, which is a set of the form A Cartesian product B, where A and B are some sets of strings, such that with the property that this set is simple given any. So I mean, so you can draw it as a like as a table or a rectangle. So A times B, and then there is a such that with the property that pi is simple given any pair from it, any pair xy from pi. So x and y are binary strings now. So simple, that is, I don't know, let's say that the complexity of pi given x and y is, I don't know, constant, for example. So okay, so for any pi like that, and then we have this inequality that complexity of pi given x plus complexity of pi given y is at most complexity of pi plus some logarithmic terms, and this holds for all x and y from pi. Yeah.
So there are two quantifiers over x and y. Pi is simple given any pair. This is true for every x and y. And then the claim is about the inequality, but it's not the same x and y. So to have this inequality true for some x and y, we need the complexity of pi given xy be small for every x prime, y prime, and pi. So it's
Yeah,
kind of bound variables, locally bound variables.
Yeah,
I don't know, is it any clear?
No, formally speaking, this x, y in the third line are bounded by quantifier, so everything is all right. Maybe pedagogically it would be better to rename them in A, B, but I think it's pretty clear.
Yeah, so let's hope that it's clear. I don't know. Well, I mean, so there is one thing, so that there is some property of rectangles that it's simple given any and I mean any pair from it. And then so I don't know, this is here. And then there is another statement that for any such pi and for any entry or any pair from it, there is this inequality. And the constant, of course, like depends what's the constant here, but not on x and y. Okay. So, and then we discussed this stuff, and then was some there was some complexity proof of it with independization, whatever trick. So no combinatorics. But on the other hand, there is a combinatorial game or something that's more or less equivalent to that statement. So let's recall what's the game. I don't know. Let's call rectangle game. In rectangle game, there are two players, mathematician and nature. Or whatever you prefer. Well, so we will be like our goal will be, something. We will play for math. And so there is a n times n table. Okay, and then what happens is that the
As
game
usual,
proceeds in
they
rounds.
move alternatively. They alternate each round.
Yes. In each round, nature indicates a combinatorial rectangle in this matrix. So like a submatrix. So some set of rows times some set of columns. A combinatorial rectangle in this n by n matrix.
If anyone knows English, should we say rectangle or what is the correct?
I believe it was a rectangle.
Okay.
Well, it depends on the X. I mean, like when you're in London, on where you are.
Where you're in London or in London? Yeah, okay.
In London or in London, rectangle.
Wow. Okay,
So
okay.
the question doesn't make any sense. Sorry, but sorry. I mean, too rude probably, but okay. In
Always
each round,
okay.
so
Yeah. Nature indicates combinatorial rectangle, and then mathematicians.
a mathematician assigns one of the two colors to it. One of two colors to it. So there are, okay, let's call somehow the colors, I don't know, let's call them X color and Y color. Okay. So this somehow corresponds that we imagine that there is like an X axis and a Y axis. So columns correspond to X's, right? And rows correspond to Y's. Okay. So the math goal, the goal of math
And
in
the
general,
rectangle should be disjoint, I guess.
I would say right away that, okay, so that every one possibility is that, okay, nature has a restriction that every entry is covered every entry of the matrix is covered some constant number of times. So you fix some constant and then you obtain, it's like a parameter of the game, and then with this constant we have this game.
And
the
game
most
is
simple
still
case is
reasonable if it's just disjoint. So this
yeah,
number
and
is
it's still
one.
reasonable if it's just this constant is just one. So not yeah. Yeah, and and how to formulate math goal? Okay. The math goal is to ensure that every column intersects just a small number. So what is bad? The bad is when we have a column that intersects a rectangle colored in Y color, like the color corresponding to the other dimension. And we want, so the math goal is to ensure that this happens just a few times for every column and then also for every row.
Intersects a small number of Y rectangles. Yeah.
Yeah,
Every
column intersects a small number
of Y rectangles.
Of Y color rectangles. And every row, so every like Y, every possible Y, intersects a small number. Every row now. Every row intersects a small number of X colored rectangles. And okay, and then it's just, it's just a goal that we have in mind, but you can make it more specific. For example, you can ask, okay, so let's say math means if every column intersects at most, I don't know, Y colored rectangles, and every row intersects at most B X colored rectangles. And then let's say, I don't know, the game also,
the number of moves, the number of rounds.
The number of rounds is T. And then, okay, let's sum up. So what we have n times n matrix. We have this number, which is a restriction of nature, that how many times every entry can be covered. We have the number of rounds, which is T. We have a restriction how many Y-colored rectangles can a column intersect, and a restriction how many X-colored rectangles can a row intersect. Right? A, B. So, and okay, now this I don't know, like 5 numbers or something define a game. And then either of the players has a winning strategy in this game. So, and now the question, yeah.
So let's stop for a while and ask whether the game is clear.
Yes.
Could you say again, what are these 5 numbers?
No, I guess it's T,
yes.
N, one more N, A, and B.
What are this N and one more N?
And just the third number equal to the second one. I just read what we have, T, N, N, A, B.
No, we have a multiplicity of covering.
Multiplicity of covering.
I got it.
Sorry,
just kidding.
Yeah,
no,
I see.
Yeah.
But actually, let's imagine that this multiplicity of covering is fixed, and N is somehow big, and T, A, B also are big. Okay, so is the game clear? Let me ask. Okay, then I ask a question. Imagine that T is much greater. It doesn't want to write. Times A times B. So the number of rounds is much bigger than A times B. Then why nature can win? Let someone say this. So if t is, of course, the more t, the bigger t is, and the smaller a and b are, the easier the game is for the nature, because she has more, or
Has
it,
more rounds.
yeah, no, has
If you are speaking anything, we cannot hear you.
No, we are
Yes,
waiting, I guess, for somebody to say something. So
No,
there was a
Sasha,
question.
no, Sasha Shen is saying something all the time, as I can see from his
Ah,
gestures. But
then I don't know what he's saying. Well, so let's try to then answer his question, right? So um so I
Jumbo
don't know, let's
has
say
disappeared.
no again. So okay, let's say I don't know that T is
Is
something
it,
bigger.
Sasha, is it okay that we cannot hear the Jamboard?
That what?
We cannot hear that Jamboard anymore.
You can yeah, that because he's was right. I can share it now, I guess. Oh, where screen? Now I'm sharing my screen.
Yep, we can see.
Mm-hmm.
Sorry, can I ask a question about math goal?
Yeah.
This condition that every column intersects a small number of y-color rectangles, does it mean that during the whole history of the game, there were only a few rectangles y-colored? Uh, does it mean that during the whole history, this condition, there's a small number, or is it like at the end, or
Only in the end? Well, I
Yeah.
mean, so this thing is so this condition is for the end, right? But I mean, then it cannot. I mean, during the game. So if you fix the column and then you look for a number of y-colored rectangles that intersected, then I mean it can only increase, right? So if in the end is it most A, then I mean throughout the game it's at most A. So that I mean
Uh,
that
Okay, then maybe I misunderstood. When we color rectangle with some color, and then we try to assign a new color to some of these cells, do we have two rectangles colored after that on these cells? I mean, doesn't it cell has a concrete one color at a time, or
no 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 cells if I understood correctly, cells do not have the color, right? So um so for example, it can be well, in principle, you can think of the case when the rectangles are disjoint, even, but let's say they might be not disjoint, and let's say this can be colored in X color, and
okay?
this can be
So there is
colored in
no
Y
such thing
color.
as recoloring, yes?
Then yeah, so then I consider this column, and what is bad for this column? For the column, the Y, this guy is bad, right? Yeah, but if it has any number of X colored rectangles, that's fine, intersecting it, because it's like X axis, right? So here's X, but because of it, this stuff is bad. But it's not so like I have a cell in the intersection of these two rectangles, but it doesn't have a color. I mean, the cells do not have a color. It's just every rectangle have a color.
Yes, okay.
All right. Yeah. All right. So I mean, so then the result is that we have so there is this inequality about Kolmogorov complexity, and let's try to state something about the game. So
Shouldn't we
the
first
game is
answer
that
Sasha's question? Like, why if t is much larger than a times b?
yeah, I wanna state the result and then we'll see. So the result says that math has a winning strategy, whenever the number of rounds is at most a times b divided by some polynomial in the size of the table. So yeah, so indeed that's the result. We can try to understand why we have a times b.
Excuse me. Maybe I feel something wrong with this statement. Maybe n must be in polynomial scale, or it seems that b is comparable with n, and if you divide
actually,
a by n,
it should be logarithm of n.
Maybe polylog n.
Okay.
So before we have strings of length n, small n. And
yeah, I think
here
log
we have and big is 2 to the small n, and polynomial is in small n. But still some poly. It's not O of log n, but poly of log n.
I think it's poly. Yeah. Okay.
Yeah,
so
yeah,
some. All right. Okay, so the statement is that math has a winning strategy when the number of rounds is at most the product of A and B, and also divided by some polylog n. We discussed even that without this polylog n, we cannot achieve this. So, but let's understand indeed a simple thing that, for example, when I don't know, when t is A times B, I don't know, 1 plus epsilon or something, then
sorry, Sasha. What's the condition on the number of overlaps?
Well, okay, that's some constant that also somehow hidden here. So I mean, let's fix some universal constant on the number of overlaps, and then all the statements will be for every constant of this overlap size, and then they will this bounds will somehow.
If you want
Do
to
you need in the proof this general case, or we can focus on the case when rectangles are disjoint?
Well, for the okay, so for the application to obtain this inequality, it's not enough of the case when they are disjoint.
I see.
No, inequality.
And I don't know how to reduce it.
Yeah, inequality, Kolmogorov inequality corresponds to a more general case where are not disjoint. Actually, then in the denominator, you should write poly of n also. Factor poly of this maximal number of maximum, how to say it, kratность, multiplicity.
Yeah, but the multiplicity is hidden in polylog.
Yeah.
Here is
so I'm just indeed that's possible, I guess, to write somehow how it depends this bound on the number of overlaps that you permit for the nature. But I mean, I'm not. I guess I'm thinking it would be more easier to follow if you just fix it. It's some constant. Yeah.
But for those who want to remember this, we can just write in an invisible color that it should be actually multiplied by polynomial of multiplicity.
Yeah, all right. So and let's try to understand that if T is A times B, then nature has a very
Can win
simple
easily.
winning strategy. I guess just we should
Just
draw.
let someone explain this. Maybe someone can.
Well, I
explain
don't know if
this.
somebody will. Okay.
But if it's so simple that if this is not clear, then the game is not clear.
Okay, I can try it.
Yeah.
So let us say that rectangles should be disjoint to keep things simple because not much changes. So the constant is 1 for multiplicity.
Yeah.
And then let's take cells from 1 by 1 and take just a rectangle of size 2a and 2b. And
So,
ask
Yeah, I think
for
like
all
that.
of
Here
them.
is
So
2A
nature can
and-
just go in one round. Yes.
And then there's B, not A.
Yeah, 2A and 2B. Plus 1, sorry, 2A plus 1, 2B plus 1.
Okay, let it be plus.
Yeah. Okay, and then we see what mathematician answers. And so we look whether it's more X columns or Y columns. And then if there are fewer Y colors, then in some
So
column.
you take many rectangles for each. For
Yeah,
each
yeah, yeah.
point in
So
this
all
thing, you take a
rectangles are 1
rectangle.
by 1. Yes, yes.
Yeah. And some of them can be X or some can be Y, but at least half of them should be of some kind.
Yeah. And then, sorry, I forgot the rule. So we have to have at most Y colors, at most every column intersect at
No,
most.
one color should not be of many in horizontal lines, and one can be not in vertical lines.
Okay, so we need to look to the color that appears most.
Yeah.
And then it will be the condition should be violated.
Yeah, and it
Yeah.
will be violated. In the corresponding direction. If more than the half of the cells has one color, then of course in some vertical the proportion is at least 1/2, and in some horizontal line the proportion is 1/2, and so we have more than A or more than B, depending on the direction.
Okay.
Yeah.
And maybe, but that's.
So you don't even need 1 plus epsilon. Just 4a times b would be more or less enough.
Okay, but well, I guess now it's reasonable to remind how to derive the inequality from the game. And then the whole thing was that the other direction also holds, that for inequality, this statement about strategy, I mean, from the Kolmogorov complexity, you can give a strategy for mathematician, but one can complain that this is a very inexplicit strategy and ask whether there is a simpler combinatorial argument.
So there are three different parts which can be considered separately, and now the audience should choose one of them. The first one is explanation why the complexity statement follows from this game the existence of winning strategy for mathematicians.
So let's write it. Complexity implies game.
Yeah. The second is why game implies the existence of winning strategy for mathematicians implies the complexity statement. No, with some polynomial reverse parameters, they are the constants, of course, are not the same here. And third thing, which was this we somehow discussed maybe, but the third thing which we never discussed is kind of interpretation of this game, how it's related to all these stories about reconciling the opinion of experts, blah, 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 and how one can try to prove the game statement, a weaker game statement, purely combinatorially using the techniques from these expert reconciliation stories. So what do you want to hear first or most?
I don't understand. Sasha wrote the theorem. Can he prove it without Kolmogorov complexity?
In this form, no.
Mm-hmm.
He can prove a weaker theorem without Kolmogorov complexity.
And what is the weaker theorem?
Weaker theorem is more or less that so first in this weaker theorem A is equal to B.
Okay.
But T but they are not square root of T as it is in general theorem. But T in the power something like 2/3.
I don't understand.
So let me try to say it. So the theorem is that math has a winning strategy for A equals B equals T to the 2/3 times polylog n. So when you allow A and B to be like T to the 2/3 and allow it to maybe some polylog n, that's a restriction for math. Then, okay, there is an explicit strategy of math that achieves this.
Just recall that the bigger A and B are, the easier is the task of the math. So the direct strategy works if the task is easier. It has T to the 2/3 instead of square root of T.
Yeah. So, for example, the old theorem. I mean, so this old. So I mean, what we can get actually is that when A is equal to B is equal to the square root of T polylog n from this theorem. But the point is that that's proved by Kolmogorov complexity and so on. This weaker statement is proved without Kolmogorov complexity.
Excuse me, just I'm confused. I'm impression that the inequality is in the wrong direction. The first theorem claims that T must be small in the sense that it must be below A times B. The second theorem claims that T must be just T
So,
compared with AB is
as I see, if T decreases, then the task for math is easier. So it's a sort of bound for this inequality.
Yeah, let's try to understand. So we are trying to say for which parameters mathematician has a winning strategy.
Sorry. Greater in other directions. This.
Yeah. Yeah, I mean, I just wrote equality. I mean, that's
the board
when A, B are equal to this thing, and of course, if they're just bigger, then for math it's just easier. Yeah, so I just wrote that A and B, when they are equal to T to the 2/3 times some polylog, then math has a winning strategy. In the first theorem, the condition is that when T is
no, excuse, still strange. Let us take this border case when A equals B equals T to the 2/3. Yeah. It means that T equals
AB times to the 4/3 or whatever. Yes. No. Yes.
T to the 4/3 equals A times B.
Yeah. Okay. So like we could try to prove something like the weaker statement would be that the math has a explicit winning strategy when this holds.
So the condition is weaker.
Sorry. 3/4, I guess. Yeah.
Then this is not what's written in your second theorem. I think 2/3 must be 3/2.
No, okay. When I have 2/3 time to 2/3 plus 2/3, it's 4/3, and then to the 4/4, it's 1, so it's fine.
So here AB is equal to 2 4/3. So here AB should be bigger. It's enough to have the product about T, but for the weaker strategy, AB should be bigger, and the product should be not only T, but also T in the power of 4/3.
Okay. Can you confirm that the second theorem doesn't follow from the first one? It says it claims something strongly in a way.
No, it's strongly weaker, so to say.
Sorry.
Okay, the first theorem claims that mathematicians can win if T is pretty small. And
Yes.
the second theorem claims that mathematician can win if T is
even smaller. Because
even smaller.
In the first theorem, T should be pretty small. It's A times B.
Okay.
And in the second theorem, T is even smaller.
Yeah. Now I see. I agree. Sorry.
Yeah.
Okay, it's okay. You're right. Sorry.
Okay, so о чем вообще вы So we have three parts. We can explain why complexity inequality implies the game statement, how the game statement implies complexity inequality, and also what is the interpretation of in terms of reconciling experts, and how this interpretation helps us to prove a weaker version of game statement than we know from complexity theory.
I vote for the third option.
Third option.
Yes, because
Okay.
the first two we have discussed
already
at some extent.
Okay. So let's try to do the third option.
Yeah.
Okay. So yeah, we have a lot of stuff.
Should move to page 9. I can tell you in advance.
Yeah. Okay, so let's write a theorem here. Mathematician has a winning strategy. When
A and B
A
are T
is
to
equal
the
to
power
B, and it's at least T to the 2/3 times some polylog on the size of the table. So that's what we are going to prove.
Yeah, and again, the Kolmogorov complexity statement makes it better. The condition weaker, just 2/3 are replaced by 1/2.
Yes, so we are proving this without Kolmogorov. And in the first step, which is might be not really necessary, but I think it like clarifies things. What will be happening is to give a slightly different formulation of what is happening. So let me try to do this. Let's consider another game. There are n people. Okay, another game. And we will reduce our initial game to that game, and in fact, they will be more or less equivalent. Another game. And n people. Then there are
again T rounds.
And there are T rounds. In each round, some people Okay, so now there will be something random, but okay, some people want to, I don't know, go to cinema, and some people want to go to a concert. But that's not all people. I mean, then some people don't care where to go.
But
They are fine with everything.
Why not to let them do
no,
what
no,
they
no
want?
one can go to cinema and concert at the same moment. Yeah.
Yeah. And
No,
moreover,
I mean, it's like
there
a
is-
group of friends that decide what to do
Yeah.
this weekend.
Moreover, this is a collectivist game. They are all forced to go in one place. The only choice is to which place.
Yeah,
They are
yeah.
not just a bus. They are already in the bus, and the bus driver will bring them either to cinema or to the concert. They should.
Yeah.
The only thing they should
No,
decide.
I mean, it's like a group of friends that want to go together, but I mean, some of them have preferences, this preference, that preferences, and then
Yeah.
some of them are fine with everything. They don't care. And so we are like, I don't know, entertainment agency, and we have to decide where they should go. So, and we decide where they go. And our goal, well, that and then, okay, in every round, some of the people will be displeased, right? So if the guy wanted to go to a cinema and we go to a concert, then he's unhappy. The day is ruined for him. And likewise, if I don't know, a guy wanted to go to a concert and everybody went to a cinema, then it's also the day is ruined for him. But people who don't care, I mean, they are fine with everything, so they are not dissatisfied. So, and then for each guy, there is a number of times out of these 3 rounds, out of these 3 weekends, when he was displeased. And our goal is naturally to make everybody displeased a minimal number of times. Our goal.
So, for example,
Make
square n to the t to the power of 2/3 times. So it's a small fraction of t. And someone should explain why our goal cannot be achieved. Probably Misha says that it's impossible because of something. Yeah.
No,
Sorry,
I don't understand the relation with the previous game. In the previous game, we have a bound on multiplicity of the covering.
We didn't come to this point yet.
Yeah.
But just for now, you can say why cannot we achieve that now each person was unhappy only t to the 2/3 times. What is the obvious example when we cannot?
So let me state more precisely. Without just like as I wrote it, there is no strategy that so somebody will it can be possible that somebody will be displeased half of the times. So when it happens when somebody is displeased half of the times.
Half of the group wants cinema, the other half wants concert.
Yes, time. Exactly. Yeah, even if I have just one pair of guys, I mean, one always wants to go to
it's
a cinema, and the other always wants to go.
And one concert goer. So they always, one of them will be displeased. So one of them will be displeased half of the time. And this is unavoidable unless we put additional restrictions.
Yeah, an additional restriction is I mean, it's like to avoid this example with two contradicting people. That restriction that every pair of people contradict each other some universal constant number of times.
So if this number is 1, then it means that if people once have contradicting opinion, then they never will be afraid of repeating such a situation again, and never will have
Yeah, and contradicting opinion, let's clarify that. That's when one guy wants just cinema and the other guy wants just the concert. So people who don't care, they are not contradicting. Neither. Nobody.
Yeah.
That's fine. So yeah.
Okay,
so that's a game. Let's try to understand I don't know. Let's try to understand the relation with the rectangle game.
So can you say it again? So if we have a constant equals 1, that means that after one time they will be agree on everything, or
at least one of them will abstain and not ask for anything.
Okay.
Just they набили друг другу морду и не хотят это повторять еще раз. Just like something like this. But the goal of the game that every person is unhappy at most t to the 2 to the 3 poly of n time, polylog of n times. Just we can say for which value of a there is a winning strategy.
Okay, no, proposition in the entertainment game we have a winning strategy for a, which is t to the 2/3 times polylog n. Now, okay, I guess the obvious thing, obvious question is,
What is
I mean,
relation?
What's the relation?
Does
But I mean, it's more or less.
Does anyone see how to derive this theorem about this game from the theorem about rectangles?
You claim that proposition follows from the theorem, not the equivalence between them.
I mean, there is even an equivalence, more or less, but in any of the direction. But the game is, I mean, the game is equivalent, but yeah. But okay, any of the directions. Okay. I guess this should be easy without any from proposition to theorem. So from this new game to the old game.
For me, this is not clear.
Well, okay, let's.
But the games are clear, both games. Just the connection is not clear. Yeah.
Yeah. Okay. So let's try to say something because it's very easy. So. So the game with rectangles is played on n times n table, and the columns and the rows will be people. So now we will model as we will have 2n people. And then when we have a rectangle, we imagine is that these columns say that they want to go to a cinema, and these columns say that we want to go to a concert. And then we have to decide, I mean, and that's the cinema and the concert, there will be our two colors. One, so, and remember that there is one color which is good for columns and bad for the rows. And the other color was good for rows and bad for columns. Well, okay.
So the reduction, if the nature gives us a rectangle, we interpret these rectangles as that among our 2n people, we have some people which want to go to cinema, which corresponds to the rows of the rectangles, and some people won't go to concert, which corresponds to the columns.
Mm-hmm.
Then the points of this rectangle corresponds to conflicting pair of peoples.
Conflicting pairs of people. Yep.
Yeah, because we can decide it arbitrarily, but we decide that this is, for example, these people are want always for concert and this for cinema.
Yeah, and then also important thing. So we have a column, and I look for a number of rectangles that intersect, well, that contain this column, let's say, right? This is like the number of times this guy corresponding to this column, I mean, had a strong opinion or something. Well, the guys who are columns only want to go to a cinema, let's say. And then when we are counting the number of rectangles that have an opposite color, it means just the number of times this guy was unsatisfied when they went to the concert. So exactly we obtain this reduction. But is it clear now?
It seems that a person can be unhappy once as a column and one more time, okay, and a few more times as a row.
No.
We
So
have
in this reduction,
we have rectangles.
Yes.
And now we create 2n people artificially. And
2n.
some of them are column or concert people, and some are cinema or row people.
I see.
No, actually, only one, they are so organized in such a way that only half of the people can conflict with the other half. They never conflict inside some.
I see, yeah, I got
inside
it.
the same half.
Something
But-
happens with the Jamboard.
Yeah, it shows interesting paper, non-contiguous pieces in adversarial bandits. No, I am afraid to start again the screening because it's probably there is a computer problem.
No, just I think the speaker switched to another tab in the browser.
Yeah, Sasha,
I'm here or what?
you are
What's
here, but
happening?
you are showing the paper
Something
online
bad?
fair. No,
You're
no.
showing a wrong tab of your browser,
Archive.org.
probably.
No problem. But you can
No.
select the probably even worse tab of your browser. So this one is still okay.
So yeah, so I guess you now see that I'm
Yeah. But
Ah.
really, can you start sharing the good.
yeah. Sorry. I just
Yeah.
I was confused.
So
What's
very
happening?
good, very good.
Okay.
So what we stopped that if we have a winning strategy for the cinema and concert game, we can provide a strategy for rectangles. And
Yeah.
for
So
that,
but
we just take the number of people equal to 2n. So is it clear or not? It's extremely simple. So if it's not clear, it should be explained. It was just badly explained.
I have a little question. You say that the game is exactly the same. So how do you do the reduction in the other direction? Or
so yeah. So in the other direction. So the point is that in the rectangle game, it's not exactly the same. You can notice that in this rectangle game, like there are guys who always want, if they want something, they go to cinema. They want to go to cinema, and
Yeah.
that's a columns. And then there are other guys that if they want to go to somewhere, then you can go. They want to go to a concert. So,
Okay, I
but
know already. You can have for one guy,
2 copies.
yeah,
Yes.
2 copies, and then this, yeah, okay.
One of them is active when the guy wants to
Yeah.
go to the cinema, and one of them is active when she wants to go to concert. So we have actually factor 2. So now if we have people who are in if we have n people, we now have to put both n people on the horizontal axis and both n people and also n people on the vertical axis. So in total we have 2n people. So this
Mm-hmm.
people.
Okay. So I guess we can try. So now the next thing is to describe a winning strategy for
is
this.
it clear or not? People are somehow. It should be. It's very easy, so it should be clear. So just who understand this? Can you I don't know, vote or raise your hand or do something? Because probably something is not badly explained. Just. No, people are unhappy.
No, some of them are happy, but not all.
Yeah.
But
No,
they
Maybe
don't know how
just
to raise the hand. Sorry.
Yeah.
Yeah,
You can
but
stay on
I
the head
couldn't.
instead
Yeah,
if you want.
yeah. I will do it like this with the camera.
Yeah. Okay. Then maybe you can, if there are at least some people who are happy with this, maybe you can explain your your argument why there is a winning strategy without Kolmogorov complexity.
yeah.
And let me say in advance that the more complicated and unclear the argument is, the better it is for Kolmogorov complexity, because the Kolmogorov complexity replaces this unclear argument, and so we get more advantages using our nice Kolmogorov complexity theory.
So are you saying that we're going to have a complicated and unclear proof in a minute?
Yes, of course.
I don't want to say this, but
You
I
did.
just say that if we will have a
No,
complicated
that's a
unclear
proof that we also. So I have to say at this moment that this is a proof.
Sasha, the proof
That's
will be unclear if you will interrupt it each minute.
Yeah, this is
So
why,
if
why
you
I'm interested in this.
give a time for a speaker to explain the proof, we can decide. But now
yeah, and the
we
proof.
can. There is no room for this decision because, of course, if your comments are more frequent than speakers' arguments, then the proof will be unclear.
No, I just want to make you and Sasha angry, because in this state you will make maximal effort to explain the proof clearly and understand it. So now you are ready, and we can proceed.
No, that's a proof. Also, it's a common with Thomas Steifer, so that's a good sign now. So yeah, so okay, what's the proof? So the idea is that in each each guy will be have its assign its displeasure. So displeasure of the ith guy after t rounds will be 1 plus, well, some number. It's like exponential function in the number of times it was displaced. Number of times I was displeased. So we measure displeasure in this way. I don't know why. So for some delta greater than 0, that will be determined later. Okay, and then in each after each round there is a total displeasure, right? The sum over all guys of these things. And the algorithm is very simple. Make decisions in a way that increases displeasure, total displeasure, how to say it, that minimizes the increase of the total displeasure. There are minimize the increase of the total displeasure. All right. So That's
Is
an
it the
algorithm.
same that minimize of the total displeasure? Why do you need increase? We cannot change the past, so
I mean, I guess that's just bad wording. What I mean is just we have a displeasure, right? Okay, let's see what happens. So so there is a round. So let's we have some some round is happening, and then in some round, some guys say we want to go to cinema, and then some guys want to say we want to go to a concert, and the other guys do not care. Okay, and then they already have some displeasure, right? What I'm saying is that I want, so, and I can either decide to go to a cinema or to a concert. If I decide that I go to a cinema, the displeasure of this guy will be multiplied by 1 plus delta, right? If I decide to go to a concert, then displeasure of these guys will be multiplied by 1 plus delta. So, and I see which of these two, and I choose an option that yields a smaller displeasure in the end. I mean, so basically, what is the option? There is a current, so I have a total displeasure now, and then there is a fraction of this displeasure that wants to go to a cinema, and then there is a fraction of this displeasure that wants to go to a concert. And obviously, I want to choose a bigger fraction, so that the smaller fraction is multiplied by 1 plus delta.
So on the first step, you just follow the majority. And on the
Yeah.
second step, you also follow almost the weighted majority. The people who was already unhappy have more weight. They are weight 1 plus delta instead of 1. But still you take the weighted majority. And then it's a natural idea. If someone were unhappy many times, then it's better not to make him unhappy once again. So
is the algorithm clear? All right. And then what we are saying that if I choose delta something like 1 divided by t to the 2/3, then let's say that after t rounds, I will have, so what I want to say, so I will have like the maximal displeasure, so the maximal overall guys, the number of times they were displeased. So, and I want to show that this is at most this plus some polylog of n. Okay. Right. So how we will show an upper bound on Dmax? So Dmax is the maximum displeasure after t rounds. Well, okay. So what we can do is that we can consider the displeasure of this maximally displeased guy, and just notice that it is at most. So we will just bound it by the total displeasure after t rounds. Okay. And then our task is somehow upper bound now the total displeasure using that our algorithm somehow chooses to does something to so that it increases not so much. I don't know how to say it. So let's now try. So now let's try to bound the total displeasure after t rounds. Well, let's try. So initially, sorry. Let's decide that initial displeasure is just 1. Okay, I forgot to say it. So initially it's 1. So it isn't usual. So initially the total displeasure is capital N, the number of guys. And then I want to somehow bound like how much it increases in each round. So let's try to understand how much it increases in the ith round. how much
So it's 1 plus delta over 2 factor.
No, that won't be enough for us. We will have to analyze. Yeah, you are right. That we can upper bound it this way, but we have to upper bound it more precisely. The upper bound. So sorry. So you're right, but I just want to say that in the ith round, remember that there was a cinema guys and concert guys. And what I did, I took a fraction of displeasure that is minimal. Sorry, I satisfied the maximal fraction out of these two, cinema fraction and concert fraction. And then the minimal of these two fractions was multiplied by 1 plus delta. So let me denote epsilon I, the fraction of displeasure in the ith round.
You
That
mean
is
the
multiplied by
fraction of displeasures, the sum of weights. It's
Yeah.
weighted fraction. It's not just the proportion of people.
So yeah, I'm saying that the fraction of displeasure. So we have displeasure. Part of this displeasure is concentrated by, let's say, concert guys, but it's smaller than cinema guys. So we go to cinema, and concert guys are multiplied by 1 plus delta. Okay, so what does it mean? So how much the displeasure changes? So it's just a variable. Yes.
And there is also a fraction which do not care. Their displeasure is not multiplied by anything.
No. Because they are not displeased. They are fine with everything.
And the people who want something and get this, of course, also keep the displeasure the same.
So
Yes.
our sum is the sum of three fractions. One of them is multiplied by 1 plus delta, and two other ones remain intact.
Yeah, so there was one, let's say, okay, like imagine that the total fraction displeasure was 1, and then it becomes epsilon I is multiplied by 1 plus delta, and the other is the same. So how much is this? It should be 1 plus delta epsilon I think. All right. So and this is just nothing happens now, because I'm just saying that I mean, this is even exactly right, because I even can write equality here, that this thing is just equal to the product of 1 plus delta epsilon 1 and so on, 1 plus delta epsilon t. This is how the displeasure changes. Okay, so what's the idea how to get something out of it? So of course we have to use the restriction that so okay, now we have to use the restrictions that each pair of guys can contradict it just a few times. Somehow from this we have to derive that this, okay, epsilon 1 epsilon t should be small, right? Because we want to upper bound this thing somehow. Okay, what's the idea that why they would be small? At least how in principle you can relate one thing to another. The thing is, so let's say epsilon 1 again. What is this? Is the fraction of guys, let's say, that want to go to a concert, and this is a minimal of the concert and cinema guys. This means that there is at least also epsilon 1 fraction of guys that want to go to a cinema. It means that, and this also means that, I mean, there is at least epsilon 1 squared fraction of pairs with this, if you consider like a product distribution, that contradict each other.
No, but when you say fraction, you should be more, fraction is kind of fraction of weight and fraction of physical people. You speak about fraction of weight, yeah?
I'm speaking about yeah, like weight, yeah. So at least okay. Well, I mean, so this current displeasure, it's just some number assigned to each guy. You can normalize it and consider a probability distribution. And then epsilon 1, it will be just a probability in this probability distribution of guys that want to go to a concert, let's say. Well, it's a smaller of two probabilities, cinema probability and concert probability. But then, since it's a smaller, then the opposite probability also has the probability at least epsilon 1. It means that if you consider product distribution on the pairs, the contradicting pairs have at least probability epsilon 1 to the square.
So before the next round, we somehow making a reweighting of the people. Their probabilities to choose each person is proportional to the amount of current displeasure of this person. And then if we then the epsilon I is the fraction of people who will be again displeased. But also the same fraction of people would be pleased, because otherwise we have chosen the other decision. And so in this strange distribution, when people are reweighted, the proportion of pairs of contradicting people is epsilon square. That's what you're saying, yeah?
Yes. Okay, so can I copy it? No. Okay, thought I can copy it.
You can copy the page if you want, or part of the page. It's all.
How I copy? I want to copy this inequality and put it on the next. Calculation, I forgot. Duplicate, and then.
Then you can go to the next page and say paste, I guess, no? At least that I would try to do.
Okay, sorry.
Okay, I try to make a thing.
Okay, sorry for that. Okay, let's and how I can okay. I thought I can do this maybe. So you're trying to copy this.
I am trying to copy, but doesn't work. Okay.
Okay. Well, okay, let's try to write it again. So we have this inequality that this thing is at most the sum of the total displeasure after t rounds, and then it is at most n times these products. Okay. Then, okay, let's take the log of this first. Now we will do some just an easy thing. So this will be log n plus the sum of these logs. This sum to t, sorry, because it's over rounds. Okay, and then the sum of the logs, we can just lower bound.
Upper bound.
Like this. Upper bound, yeah. Sum of epsilon i's. Now, this thing log of 1 plus delta, I already told that delta will be like something that goes to 0. So that will be more or less like delta. So this would give us something like d max is at most log n divided by delta plus the sum of epsilon i's. And now again, our task is to upper bound the sum of epsilon i's.
And the only thing we have, the only tool for that is just to connect them with the probability of the number of contradictions.
Yes, and I already told that it will be through squares. So the first thing that I want to use is the Cauchy inequality. So the sum of this, I don't know, divided by t is at most this thing. Now I want to somehow divide upper bound the sum of these squares. It'd be useful to divide it by t. Okay. So what I will do is that I will say that this is I will say that this is a probability of something. Sorry. Let me see. Let's consider the following probabilistic process. Consider a probability distribution. So we choose first uniformly at random around in our game. And then in this ith round, I have a displeasure distribution of displeasure. And if you normalize it, it gives me a probability distribution. Then what I'm doing, I'm choosing two people, X and Y, independently from the displeasure distribution in the ith round.
So it's the same distribution for which we computed the probability epsilon I and another probability which was greater than.
Yes, and then the whole point is that this thing, this sum of squares divided by t, so divided by t is at most the probability that X and Y contradict in the ith round.
No, I don't understand. If you I is a bound variable or what?
What?
So
X and Y take values in the set of people.
Yeah, but
so once again, what happens? You take a random I, and this corresponds to the division by t. Now, if I fixed I have a distribution of displeasure. If I normalize it, I get a probability distribution. And then I sample independently two people with this probability distribution, and I call them X and Y. And now, as I noticed that already, if I have the ith round, there was epsilon I of guys that want to go, for example, to a concert, and at least that many guys, probability of the other guys that wants to go to a cinema. This means that if I sample two guys,
I am asking a very, very simple question. But there is there is some quantity in the right-hand side. Does it depend on I or not? This big
what
I,
does
which
it
is
mean depend
mentioned
on
there.
I?
No, there is a variable I. X and Y coincide in the ith round. So we have some probability for every round. But then what do? We sum these probabilities.
Sasha, no, we do not sum. We take a number of rounds at random. It's capital I. So we consider the following process. We choose a number of rounds at random. We choose 2 random people, and we wonder where they contradict to each other. And that's the right-hand side, the probability of this event.
Yes. So it's just three mutually distributed random variables, and we consider this some events like that. And we notice that this is an upper bound on this sum. Now, the idea is that now to bound this probability under any fixation of pairs x and y. So I fix 2 people, small x and small y, and I consider a probability that x and y intersect,
contradict,
in the ith round.
Contradict, Sasha?
Sorry?
Contradict, maybe contradict?
Oh, sorry, contradict, yes. So I just consider this probability and consider any fixation of capital X and capital Y. And I want to show that this is small. What's the idea? So what happens? I fix 2 people, and then there is some, how it's called, conditional distribution of I, which is around. This number from 1 to t. And then we are interested in the probability. Well, what is the probability? And then we consider in the rounds where x and y were contradicting each other. We know that there are just a constant number of such rounds. The problem is that this conditional distribution of I is not uniform anymore when I fixed a pair of experts. Otherwise, I could say that this probability is just small o of 1 over t.
Sasha,
but the life is not that easy.
Why it is not uniform?
Well, let's try to imagine. So you have like a parallel. I don't know how it's called. A 3-dimensional rectangle or something.
Box.
So these are rounds. In each round, you basically have some distribution. You have slices that correspond to pairs of experts. And in each, you have some distribution on experts. But they are different in different moments, right? This means that
so your variables are dependent actually. I thought that I is independent on x and y, but it's not the case.
No.
Because the distribution on the pairs x, y depends on I. It changes round to round.
The I was chosen first, but still x and y are dependent on I, and so I is dependent
and so the other way around. I is dependent of on x and y.
So the point is that, okay, if I fixed a pair of experts, this is like I fixed a line here, and then the conditional distribution over rounds is proportional to probabilities of these pairs of experts in each of the round. So the more, so we have T probability distribution, and the conditional distribution on the rounds is proportional to the probability of the pair x and y in the ith round, right? And somehow we have to show that no constant number of rounds can have large probability. Although this is not uniform, we want to show, our goal is to show this somehow. Well, how would we show this? The main observation is that these probability distributions, if I make one step, one more round, they change just a little. So more or less, okay, what can happen with it? So we take displeasure and we normalize it. Okay, so what can happen with the displeasure of one guy? It can be multiplied by 1 plus delta, or not multiplied. Okay, that's fine. And then the total sum of the displeasure can be multiplied by 1 plus delta, let's say, at most, or stay the same. It can only increase. So, and then, okay, the probability of every pair, it will be the, I don't know, the displeasure divided by the sum of x plus the times displeasure of y divided by the sum. So it's like the product of and division of 4 things. Each of these 4 things in one round, they change by at most 1 plus delta factor. So I don't know, the whole probability changes by at most 1 plus delta to the, maybe it's, you can even bound it better, but okay, for simplicity, at most 1 plus delta to the 4. And the point is delta is small. It's like, it's 1 divided by t to the 2/3. Now, what's the thing? The thing is, it means that if in my conditional distribution there is a maximal probability p max, right? Then this thing is at most O of p max, right? Because we have constant number of rounds and all of them have probability at most p max. But through this p max, for example, I have, for example, a lot of things to the right. And each time there is a p max, but next probability is at least p max divided by 1 plus delta to the quarter. So I have p max. Then if I have p max, I should also have to the right p max divided by 1 plus delta to the 4. Then in the next step, I should also have p max divided by 1 plus delta, well, the square of this, 8, and so on. And this I have to have at least, I don't know, t times. T half times, I don't know, if either to the left or to the right, I have at least t over 2 rounds from this p max. So it will be something like that. But still this is at most 1. So I can bound this p max as 1 divided by this series. So, okay, at this moment, is it clear what's happening or not?
It is. I actually lost how you obtained 1 plus delta to the 4, but the remainder is clear.
So the statement is that these probabilities obtained by normalizing displeasure, every probability changes by at most this factor.
And why is this?
So this is not clear, right? Why it changes by at most this factor.
This is not clear.
Because, okay, because each probability of an expert is what? It's displeasure of this expert in the t round divided by the sum of displeasures.
So this, right?
And the same, we have like some other y divided by the sum of displeasures. Now, so you have 4 things, this, and this. I'm just saying that in one round, every of these 4 things changes by at most a factor 1 plus delta. Well, this can be multiplied by 1 plus delta or not multiplied. This can be multiplied by 1 plus delta or not multiplied. And then these sums also in each term can be multiplied by 1 plus delta, so everything changes just by 1 plus delta. at most.
No, maybe what is confusing that you have two factors in the numerator and two factors in the denominator, and you still multiply all of them, which will be more logical to say that just as 1 plus delta over square. If each of
because it's an unnecessary, complicated additional step of thought that I don't want to do.
Okay.
I want to think that some of it maybe only decrease, increase, I don't know. I guess you're right that
if the numerator and denominator can increase at most by 10%, then the fraction can increase at most 20%. That's true, but it's a bit complicated to understand. Yeah.
Okay, okay, let's skip it. Let's go forward, go on.
all right. So okay. So so we can bound Pmax in terms of this in this series. So okay, let's wave some hands now. Imagine that this series was just infinite. What is the more or less as a function of delta? What is the sum of this series? So it's like 1 divided by 1 minus the denominator, how it's called, of this series, right?
The
Ratio.
ratio. Right.
Ratio. So here, let's see. So delta goes to 0 in our case. So it is something small. So this is 1. This is some function in delta which has limit 1. And more or less, you can check that its derivative is positive. So more or less, this is like 1 divided by delta. So from which we obtain that Pmax, well, maybe some O, let's write it more precise. That Pmax is O of delta.
1 divided by 4 delta, more or less, because 1 plus delta to the fourth is 1 plus 4 delta, and then we get 4 delta.
That's why I didn't care about square, 4, whatever, because it's just some constant here, but it won't matter for us. Okay, so I kind of well, it's not an infinite series, but we will see that's enough terms to already have this. Let's keep this technical step. Let's see that there are like t terms in this infinite series, and there will be enough of them. There will be more than enough to already have the sum close to the sum of the infinite series, like that. Okay, so what we have, that Pmax, okay, let's try to, is O of delta. We have to remember that. Then if we go somewhere here, we obtain that, okay, so we obtain that under any fixation, this conditional probability is at most O of Pmax, which is O of delta. So all of this is O of delta. You see this sum of squares divided by t. And then if we'll go here, we obtain that the sum of just ai's is at most t divided by square root of delta. Well, and there is some constant also. And now we have the Dmax is at most logarithm n divided by delta plus some constant like t square root of delta. And if delta is t to the 2/3, then that's exactly how I obtain 2/3. Meaning that this and this will balance each other. Oh, sorry, I mean minus 2/3. So it's 1 divided by 2 to the 3rd. Then this will be 2 t to the 2/3, and this will be t times t to the minus 1/3, which will be t to the 2/3. And then the only technical thing that remains is that if I take a look at this infinite sum, this series, so here delta is about 1 divided by 2 to the 2/3, and in fact there will be enough to take not even t terms but t to the 2/3 terms to already be, something close to this 1 over delta. Yeah, so this is it.
No, actually, why t to the 2/3 is just not square root of t.
Well, because we have to normalize 1 of the delta should be equal to t square root of delta, meaning that
So delta is not proportional to 1 over t. That's yeah. So you said in the beginning
meaning
the
that
delta will be 1 over t, but it's not exact.
what?
So you said in the very beginning that you will later take delta close to 1 over t, and this is
No, I haven't said that. I take delta to be this.
Yeah, and yeah. So you need more or less that many terms to get almost full sum in the geometric series.
Yeah. And I have more than enough, which shows that this argument somehow is not optimal.
Yeah,
and maybe.
And you have t at least on one side. You have at least t. So, yeah. Okay, so now it seems that the proof is more or less finished. Are there any questions, comments, or is it clear or is it not clear?
So I missed the beginning, and now on the slides I see that this was the proof without Kolmogorov, right?
Yeah, that's an entire point.
And
yeah.
was it another proof before?
No, we discussed it last year, but so and it was not repeated today, but it can be. But yeah, but maybe since Thomas is here, maybe he can comment something on this proof, or do you agree to share the responsibility for it, or then
No, Sasha, what is I don't understand the meaning of this question. What should be the answer? What are possible to answer? I think it's fine if Thomas just said that he shares no responsibility for that.
Yeah, it's
and
fine.
I don't know. So
it's fine.
What
No.
I don't know. What's the purpose of this question? You can ask whether he checked, I don't know, this proof or what.
No.
Maybe that's reasonable.
If he says yes, then I will ask him what he thinks about the possibilities to improving the bound. But if he says no, I will have no other questions. He is not guilty then and can go free.
Well, I can say that I tried to improve the bounds and failed, but I'm also not an expert in combinatorics, so I wouldn't use this as an argument for no existence of combinatorial proof.
But I guess you have some kind of motivation for this proof from this expert aggregation theory. Or I don't know who has this motivation, but maybe you can say something how it's related. Just a few words.
Well,
there are
I guess it's
two guys which Sasha called. I forgot the names from expert conciliation theory. which were mentioned as a source of inspiration.
Yes, so I guess I don't know if it's easier for me to tell it or for someone who has the whiteboard, but in expert aggregation, what we are really interested is to, so there are some experts and we assume that one of them is good in predicting, but we don't know which one. And we can use this kind of weighted average or weighted majority vote to be on average to get a probabilistic algorithm which has is close to the best learner. So it's close in a sense that it's better than linear, which is already not obvious. And what we are doing here is kind of a symmetric argument, because we can think that if we are able to predict as good as the best learner, best expert, then we can also think that we have a strategy that that this gives a strategy for the nature to beat the best learner. And I guess this is what we are doing here.
So you fold some technique from the expert theory, which uses also the weighting the experts.
Basically, Sasha, in these terms, we can say that there is a very good known algorithm that makes sure. So we discussed that it is impossible to satisfy, T over 2. It can when the guys just say the opposite. You cannot guarantee that all guys are displeased less than T over 2 times. But in the classical algorithm of Littlestone, basically the same algorithm can guarantee you that, any constant larger than 1/2, you can guarantee. Like 0.59 times T, everybody is at most displeased. But it's linear. It says that at most 1/2. You can get any constant bigger than 1/2.
And then you use the restriction of the number of conflict to improve this bound and see that what you get out of it. And this is T to the 2/3, yeah?
Yes. So just the same algorithm. Well, another delta. You have to choose delta for this specific setting. But it's a well-known thing.
Yeah.
The algorithm itself.
And also there are some strange, there is more philosophical question. There are other strange tools which we once heard at our seminar very, very long ago, which is called perturbed leader or Wolf aggregation algorithm, or there is entire bunch of different techniques. So do you believe that one of them can somehow be also used and give something better, or?
I don't know. I have to just learn what it is.
My understanding is that Wolf's aggregation is just the same idea.
But no, there is a problem. So here we have binary prediction, and this aggregation is continuous prediction.
That's another thing, yes.
But you can say, okay, let's choose one of the two sides with certain probability, and then all these techniques can be applied with probabilistic argument. But then the question is, okay, what is challenged here? So we know from other proof that there exists a strategy that works if we know all the moves of nature in advance, and then we want to transfer to online game. And so these methods gives us a way to make transformation. But if we allow probabilities, it's easy anyways with probabilistic strategy.
So I have to go.
Understand from high level reasoning.
Continue without me.
Yeah.
Okay.
So Bruno, you think that this makes this what is the hope? Is there a hope to use this technique to get t over 1/2 square root of t, or it is some kind of obstacle which
No. What I'm saying is that these methods are unlikely to help, because whatever they give us, we can get it easily with probabilistic argument that can make something random. And as I remember the proofs, it just yeah. So it's my sorry. Okay, I should
so
not
if,
speak
no,
if
but
I'm not
if
certain.
if you think there is a simplification of this argument, it's also nice. But even
No, I'm saying that these advanced things will not help to make the bound, are unlikely to help to make the bound tight. Because there is some obstacle, and to go around it, we use something that we could have used probably directly.
Yeah. Okay, but then just I can say as a closing remark that Peter Gatch believes that there should be some direct combinatorial argument. It's impossible that we indeed need Kolmogorov complexity in such a combinatorial situation, but just one should invent this argument. So this is a challenge which would be very nice that if someone comes with such an argument.
Yeah, okay, Sasha Kozaczynski already left, but if there are two proofs for something and they both have advantages, and so then you should put the proofs next to each other and match them line by line, and then see where is the trouble. It's a very normal thing to do.
It's a very normal thing, but complexity proof actually is quite complicated. There is a trick of Ramazan trick of
but it doesn't matter. It's a matter of patience. You know, if you sit maybe a week or something about it, then you can match every line in both proofs. And it's a very good way to start the research. So it means, okay, Sasha Kozaczynski left.
No,
it's
I can provide you. I
but
can provide you with the complexity proof, and you can watch it. I can easily explain it during the entire week.
But Thomas is laughing. He understands what I'm saying.
Yeah. Okay.
So he knows what needs to be done. So I will not do it.
I have a question. In many cases, it's easier to find a reasonable combinatorial proof if we have a reasonable motivation for the combinatorial question. Can you explain why do we care about this combinatorial statement?
No, if you want some formal, some plausible explanation, is just imagine this is a kind of very important question: how to conciliate the opinion of different people without making this unhappy. Very important practical problem, and then we study the boundaries for the possible solutions of this very important practical problem.
Not convinced.
Okay, but
there is a theorem with two dirty proofs, and so the question is, can we make a nice proof?
Seriously, if you can see that it is somehow connected with some natural geometric question, or I don't know, with communication complexity, or with something, maybe this will provide us with an alternative point of view, and this point of view could help to find a nice natural proof. Why not?
No, there is original motivation. This corresponds to the fact that the triple information for partition is non-negative, but if that you already know, so no new things here. Okay. So any other comments? Okay. Do we have some volunteers to give a talk for the next time?
Sasha, I would remind you that I wanted to talk about that Vapnik-Chervanenko stuff.
Okay, so you are ready to do it next time.
Right.
Good.
Mhm.
Good. So just send the announcement.
Okay.
And it's better probably to do it not just more or less today or tomorrow, so people
On
get
Friday.
it in advance. Sorry?
On Friday.
No, it's better now. At least the
Okay.
announcement. Maybe without
Okay.
without the abstract, just to people let people know that it will happen.
Okay.
Yeah. Okay. Yeah. So let's then wait for the next week.